The topic what we are going to discuss in this video lecture is the very basic building block of a robo, where it is nothing but sensors. And this is Dr. S. Lakshmi, Professor and Head Department of ECE from Rohini College of Engineering and Technology. On completion, the students will be able to classify the sensors used in robots. They'll be able to explain the operation of various sensors. They'll be able to understand where really the sensors are used in robots, and we'll just see an overview. Okay, like what why robots need sensors and how it is classified, and we'll see an overview of various sensors. So seeing this picture, you could see where is the crop line. So you could see a crop line over here, so where the sensor would detect the edges where it is used in autonomous harvesting. Similarly, you could see in a maze, so this is nothing but where I need to spot in an environment. So where am I? So in that case also, the sensor will be used to detect any the path which is open or closed. And robo sensors, it constitute robo's window to the environment. Uh, the robo needs sensing to be an active participant in the environment. Each sensor is based on a transduction principle, that is, converting an energy from one form to another. So, these sensors will measure a physical quantity. They do not provide the state. So, how these sensors are classified basically? So, here we have proprioceptive and exteroceptive, which means that which defines it as an internal state or an external state. And so in the first case, it is actually it will measure the values internal to the system, that is to the robo. Say for example, wheel position, joint angle, battery level. And once it comes to the external state, these observations of robo environment or objects present in it. And similarly, the sensors can be classified as active and passive. So, active sensors will emit energy, whereas the passive will receive energy. Say, example, the very good example of passive sensor is camera. And this table shows you what is the general sensor classification. So you could see the tactile sensors, wheel motor sensors, and you could see heading sensors. And here we can see that it is divided whether it is representing a state which is internal state or external state. And similarly, you can see that whether it's an active or passive. And this again shows all the thing which is related to the sensors, either is a ground based or motion based or vision based or active ranging sensors. So you can go through this table, and once you are characterizing any sensor performance, so we know that in any real world environment the measurement is always error prone. So we have various characteristics for the sensor, which are listed as dynamic range, which is nothing but we use it between a lower and the upper limit. The range, again, it is a minimum and a maximum differences. Resolution, it is actually the minimum differences between two values. Linearity, it is the variation in the output signal as a function of input signal. Bandwidth of frequency, it is the speed with which a sensor can provide a stream of readings. And here they are specifically relevant for real world environments, these characteristics. So either sensitivity, cross sensitivity, accuracy, systematic or deterministic error, random error, reproducibility. So we have the various definitions I've listed over here. So what do you mean by sensitivity? What is cross sensitivity? What is accuracy? And other factors. And this saw some of the pictures where you could see the different types of sensors, which is tilt sensor, where you have a mercury tilt switch, and here you can see a dual axis inclinometer. So these are the pictures which show you the sensors. And this is a potentiometer. Of course, everyone are familiar with this potentiometer. So this potentiometer, once it is moved or once it is rotated, obviously the resistance also will change. And these are some of the examples of microswitches where it is single direction or omnidirectional, which means that it can rotate in different all the directions, and roller contactor switch. And this is light sensors. Of course, we are familiar with the light sensors, which you would have done in our basic courses, which is a photoresistor, photodiode, differential photodiode, phototransistor, and you could see in this picture the various two types of sensors are represented. And thermal sensor. So it is otherwise it is called as a thermistor. Of course, we know that once the thermal temperature varies, the resistance also varies. And this is proximity sensors. Proximity sensors will be used to detect where the device or the object is located, whether it's a near or far. So normally it is a non-contact, and devices that can be used in these areas that are near to an object can be sensed. So the good examples are photocells, capacitive sensors, inductive sensors. You can see in the picture we have a IR detector and IR LED emitter. Okay, so where the LED will emit and similarly the detector will detect these light, and obviously this is related to the detected object. And here also you can see the photocells where again it will be having a pattern of LEDs and receivers, which is a phototransistors. And we have different type over here. So where you can see in the last one, which is a through beam detectors. Okay, so where the beam will detect, beam get rippled and this gets detected. And the capacitance proximity sensors. So once you talk about capacitance, obviously it will generate an electrostatic field. So you can see in the picture it consists of a probe, oscillator, filter, output circuit. So in absence of a target or object, the oscillator will become inactive. So once a target is approaching, the capacitance automatically rises, which will trigger the oscillator. This is the basic principle of capacitance proximity sensors. And very good example of these sensors where it is used. Say for example, when it is properly calibrated, so this could even detect a higher dielectric material through any lower dielectric material. So this is used very particularly, say for example, suppose I want to detect the H2O, that is a water level in the bottles. Position sensors. Position sensors, obviously, this can be detected in three ways, or three sensors can be used, which is potentiometer, which we have seen already, resolver, optical encoders. So the optical encoders will detect either a relative position or an absolute position. So here these are wheel or motor encoders. So this will measure the position, speed, direction of revolution of the wheel. So we define this as a odometry. So which is nothing but the wheel movements can be integrated to get an estimate of the robo's position. So this resolution will vary from will have a resolution of 2000 increments per revolution. So this can be either revolute or that is relative or absolute. So we have optical encoders. So the name itself suggests it involves a light. There will be a light sensor. Then there will be a decode circuitry, obviously. And there is a in between you will be having a mask or a diffuser. So this will detect the relative position where you could see this diffuser will tend to smooth these signals. This is how it is made. So it is like this will tell you the direction or the resolution. So you can see here you have a square wave generated which is denoted by A, and similarly we have one more which is denoted by B. So here the A is lagging the B, and phase lag between A and B is obviously it is from the figure you could see it is only 90 degree. So from this you could detect both the direction as well as the resolution. So these are the possible states. So A and B we have. Four different states defined: S1, S2, S3, S4. So we have the combinations of A high and low, that is high low, high, low high, and low respectively. And this is where how you detect a absolute position. So you have an LED source and you have a beam expander. So the LED will be emitting a light which is expanded, and it is called through the collimating lens and the cylindrical lens. So this is taken to a multi-block encoder disk where it is detected at the other side, such that it will be the light gets focused such that it get you could find a very absolute position. And the next type is a heading sensors. So this can be a proprioceptive, that is, or exteroceptive. So I'll allow this will allow together with appropriate velocity information, which will integrate the movement to a position estimate. So this procedure is called dead reckoning. So where this is used to determine the robot's orientation, that is, in which direction is trying to move, and inclination, how what is the angle of movement. And this is accelerometer. Of course, we know the definition of acceleration, where the force is equal to mass into acceleration is defined. A sensor will be made to sense the acceleration by simply measuring the force on a mass. So the force can be this can be done or sensed through magnetic, capacitive, or piezoelectric. Thank you.